Question 1. Consider a scenario where a company is designing a new generation of lightweight, durable outdoor equipment. To align with the principles of ISO 14009-2020 regarding material efficiency and the integration of environmental aspects into product design, which of the following approaches would most effectively minimize the environmental burden associated with material selection and utilization throughout the product's life cycle? Option A. Opting for the lightest possible materials available, even if they are single-use plastics with minimal recyclability, to reduce transportation emissions during the product's use phase. Option B. Prioritizing materials that offer superior tensile strength and abrasion resistance, even if their processing involves high energy consumption and limited end-of-life recovery options. Option C. Focusing on the use of recycled content materials, regardless of their performance characteristics or the potential for hazardous substances to be reintroduced into the product. Option D. Selecting materials that balance performance requirements with lower embodied energy, ease of processing, durability, and a high potential for closed-loop recycling or effective end-of-life management, while also considering the avoidance of hazardous substances. The correct answer is B. Prioritizing materials that offer superior tensile strength and abrasion resistance, even if their processing involves high energy consumption and limited end-of-life recovery options. Explanation: ISO 14009-2020 emphasizes a life cycle perspective for integrating environmental aspects into product design and development. Material efficiency, a core tenet, involves minimizing the quantity of materials used and maximizing their value throughout the product's life cycle. This includes considering the environmental impact of material extraction, processing, use, and end-of-life management. For a hypothetical scenario involving the development of a new portable electronic device, the principle of material efficiency would guide decisions towards selecting materials that are lighter, require less energy to process, are durable to extend product lifespan, and are readily recyclable or reusable. This aligns with the directive to consider the environmental performance of materials from cradle to grave. For instance, choosing a bio-based composite over a virgin plastic might reduce reliance on fossil fuels and lower embodied energy, provided its life cycle impacts are thoroughly assessed. Furthermore, design choices that facilitate disassembly and component recovery contribute to material efficiency by enabling reuse or recycling, thereby reducing the need for new raw material extraction. This proactive integration of material efficiency principles from the outset of the design process is crucial for achieving the environmental objectives outlined in ISO 14009-2020, moving beyond simple compliance to a more holistic approach to sustainable product development. Question 2. A nascent enterprise is developing a novel portable audio player and seeks to embed robust environmental stewardship into its product design process, adhering to the principles outlined in ISO 14009-2020. Given the inherent complexities of electronic product life cycles, which life cycle thinking (LCT) strategy would most effectively guide the integration of environmental considerations from raw material sourcing through end-of-life management for this new device? Option A. Implementing a comprehensive cradle-to-grave life cycle assessment (LCA) during the conceptual design phase to identify environmental hotspots and inform material selection, energy efficiency targets, and end-of-life strategies. Option B. Conducting a simplified eco-design checklist based on common environmental concerns without performing a detailed analysis of the entire product lifecycle. Option C. Focusing solely on end-of-life recycling processes and material recovery, as this phase typically presents the most significant waste management challenges for electronics. Option D. Prioritizing the reduction of packaging materials and transportation impacts, as these are often the most visible environmental aspects to consumers. The correct answer is A. Implementing a comprehensive cradle-to-grave life cycle assessment (LCA) during the conceptual design phase to identify environmental hotspots and inform material selection, energy efficiency targets, and end-of-life strategies. Explanation: the question asks to identify the most appropriate life cycle thinking (LCT) approach for a new portable electronic device manufacturer, aiming to minimize environmental impacts across its entire life cycle, considering the specific context of ISO 14009-2020. ISO 14009-2020 emphasizes integrating environmental aspects into product design and development, promoting LCT as a core methodology. This standard guides organizations in considering environmental impacts from raw material extraction through end-of-life management. For a new product like a portable electronic device, a proactive and comprehensive approach is essential. Evaluating potential environmental burdens at the earliest design stages, such as material selection, energy consumption during use, and recyclability, is crucial for informed decision-making. This aligns with the precautionary principle and the goal of preventing pollution at the source. Considering the life cycle stages of a portable electronic device, significant impacts can arise from resource depletion, rare earth minerals, energy use during charging and operation, and the generation of electronic waste e-waste. Therefore, a method that systematically assesses these impacts from cradle to grave, allowing for design adjustments to mitigate them, is paramount. This involves understanding the environmental hotspots across all phases, from the extraction of raw materials for components, through manufacturing, distribution, consumer use, and finally, disposal or recycling. The aim is to identify opportunities for improvement, such as using recycled materials, designing for energy efficiency, extending product lifespan, and facilitating easier disassembly and material recovery at end of life. This holistic view is the essence of life cycle thinking as advocated by ISO 14009-2020. Question 3. A manufacturing firm is designing a new line of consumer electronics and aims to maximize the use of recycled plastics. According to the principles outlined in ISO 14009-2020 for integrating environmental aspects into product design, what is the most critical factor to evaluate when selecting recycled plastic feedstocks to ensure genuine environmental improvement? Option A. The aesthetic consistency and color uniformity of the recycled plastic, as this is paramount for consumer acceptance and brand perception. Option B. The cost-effectiveness of sourcing recycled plastic compared to virgin materials, as this directly impacts market competitiveness and adoption rates. Option C. The energy and chemical inputs required for reprocessing the recycled plastic and the potential presence of hazardous substances that could leach or be released during the product's use or disposal. Option D. The volume of recycled plastic available from local suppliers to minimize transportation-related greenhouse gas emissions during procurement. The correct answer is C. The energy and chemical inputs required for reprocessing the recycled plastic and the potential presence of hazardous substances that could leach or be released during the product's use or disposal. Explanation. ISO 14009-2020 emphasizes the integration of environmental considerations throughout the product lifecycle, from conception to end of life. When incorporating recycled content materials into product design, a key consideration is ensuring that the recycled material itself does not introduce new or exacerbated environmental impacts that could undermine the initial benefit. This involves a holistic assessment that goes beyond simply substituting virgin materials. For instance, the processing required to reprocess the recycled material might consume significant energy or generate hazardous byproducts. Furthermore, the quality and consistency of recycled materials can vary, potentially affecting product durability and lifespan, which is also an environmental performance indicator. Therefore, a thorough evaluation of the entire value chain associated with the recycled content is crucial. This includes understanding the source of the recycled material, the methods used for its collection and reprocessing, and the potential for contaminants or degradation that might impact the final product's environmental profile or human health. The standard advocates for a proactive approach, where potential environmental burdens are identified and mitigated early in the design phase, aligning with the principles of eco-design and circular economy. The goal is to achieve a net positive environmental outcome, not merely a shift in impact. Question 4. A multinational electronics firm, Innovate Tech, is developing a new line of smart home devices. They are operating under the principle of extended producer responsibility (EPR), and are seeking to align their product design and development process with the guidelines of ISO 14009-2020. Considering the lifecycle perspective mandated by the standard, which design strategy would most effectively minimize Innovate Tech's future end-of-life management obligations and environmental impact, while also anticipating potential regulatory shifts like increased landfill taxes or stricter e-waste directives. Option A, focusing solely on energy efficiency during the use phase, assuming end-of-life management will be handled by external recycling services without design input. Option B, incorporating a high percentage of recycled content in all components, regardless of their recyclability at end of life. Option C, prioritizing the use of easily separable, high-grade recyclable materials and designing for modularity to facilitate repair and component reuse. Option D, developing a proprietary, complex material composite that offers superior performance but is difficult to disassemble and recycle. The correct answer is C, prioritizing the use of easily separable, high-grade recyclable materials and designing for modularity to facilitate repair and component reuse. Explanation: the core of ISO 14009-2020, particularly concerning extended producer responsibility, EPR, is the proactive integration of environmental considerations throughout the product lifecycle, from conception to end-of-life management. This standard emphasizes a design-for-environment approach, where producers anticipate and mitigate potential environmental impacts. EPR, in this context, shifts the responsibility for managing products at the end of their useful life from consumers and public authorities back to the producers. This includes the collection, recycling, and disposal of products. ISO 14009-2020 guides organizations to consider how their product design choices will affect downstream environmental management, such as ease of disassembly for material recovery, the selection of less hazardous materials that comply with regulations like the EU's Restriction of Hazardous Substances (RoHS) directive, and the potential for product refurbishment or remanufacturing. The standard advocates for a systematic approach to identifying and evaluating environmental aspects, which directly influences EPR strategies. For instance, designing a product with modular components that can be easily replaced or upgraded enhances its lifespan and reduces waste, thereby lessening the producer's end-of-life burden. Similarly, choosing materials that are readily recyclable or biodegradable aligns with EPR principles and facilitates compliance with evolving waste management legislation. The successful implementation of EPR, as facilitated by ISO 14009-2020, requires a comprehensive understanding of material flows, energy consumption, and waste generation throughout the entire product lifecycle, ensuring that design decisions contribute to a more circular economy and reduce the overall environmental footprint. Question 5. When a design team is tasked with developing a new portable media player, and they are applying the principles outlined in ISO 14009-2020 to integrate environmental aspects into the design process, what approach should they prioritize when identifying and evaluating the significance of potential environmental aspects associated with the device's entire lifecycle, from raw material extraction to end-of-life management? Option A, focus primarily on the energy consumption of the device during its use phase, as this is typically the longest phase of the product's life and directly impacts the consumer. Option B, concentrate on reducing manufacturing waste and emissions, as these are the most controllable aspects within the company's direct operational influence. Option C, give precedence to aspects that are most easily measurable and quantifiable with current available data, even if other aspects might theoretically have a greater long-term environmental consequence. Option D, prioritize aspects with the highest potential for significant environmental impact across the entire lifecycle, considering factors like resource depletion, hazardous substance release, and end-of-life recyclability, even if they are not the most obvious during early design stages. The correct answer is D. Prioritize aspects with the highest potential for significant environmental impact across the entire life cycle, considering factors like resource depletion, hazardous substance release, and end-of-life recyclability, even if they are not the most obvious during early design stages. Explanation: the question assesses the understanding of how to prioritize environmental aspects during the product design phase, specifically within the context of ISO 14009-2020. The standard emphasizes a systematic approach to integrating environmental considerations throughout the product lifecycle. When evaluating environmental aspects for a new electronic device, A crucial step is to identify those with the most significant potential environmental impact. This involves considering various factors such as the materials used, energy consumption during use, and end-of-life disposal. The directive in ISO 14009-2020 is to focus efforts on aspects that are most likely to cause harm or contribute to environmental degradation. This often means looking beyond immediate manufacturing concerns to broader life cycle impacts. For instance, while the energy efficiency of the device during its operational phase is a significant factor, the potential for hazardous substances to leach into the environment during improper disposal, or the depletion of rare earth minerals required for its components, can represent more profound and long-term environmental risks that warrant higher prioritization in the design process. Therefore, a holistic assessment that considers the entire life cycle and the severity of potential environmental consequences is paramount. This aligns with the principles of eco-design and sustainable product development, aiming to minimize the overall environmental footprint. The process involves identifying, analyzing, and evaluating these aspects to inform design decisions and mitigate potential negative environmental outcomes. Question 6. A manufacturing firm is developing a new line of portable electronic devices. To align with ISO 14009-2020 guidelines for integrating environmental aspects into product design, what fundamental approach should the design team prioritize to ensure the most significant and sustainable environmental improvements throughout the product's life cycle? Option A. Systematically identifying and addressing potential environmental aspects and impacts from the earliest conceptualization stages through end-of-life management. Option B. Focusing primarily on reducing energy consumption during the product's usage phase, as this is often the most significant environmental impact. Option C. Prioritizing compliance with current environmental regulations for component sourcing and disposal, without extending efforts to other life cycle phases. Option D. Conducting a comprehensive life cycle assessment only after the product design is finalized to identify areas for retrospective improvement. The correct answer is A. Systematically identifying and addressing potential environmental aspects and impacts from the earliest conceptualization stages through end-of-life management. Explanation. The question probes the understanding of how to effectively integrate environmental considerations into the product design and development lifecycle, as guided by ISO 14009-2020. This standard emphasizes a proactive approach, moving beyond mere compliance to achieving genuine environmental performance improvement throughout a product's existence. The core principle is to embed environmental thinking from the initial concept stages, influencing material selection, manufacturing processes, product use, and end-of-life management. Considering the principles of environmental management within product design, a key aspect is the systematic identification and evaluation of environmental aspects and impacts. This involves a life cycle perspective, acknowledging that environmental burdens can arise at any stage. For instance, material extraction, manufacturing energy consumption, transportation, product usage efficiency, and disposal methods all contribute to the overall environmental footprint. Therefore, a strategy that prioritizes early identification and mitigation of potential environmental issues, such as resource depletion or emissions, is most aligned with the standard's intent. This proactive stance allows for more impactful design choices, potentially leading to reduced waste, lower energy consumption, and the use of more sustainable materials. Such an approach fosters innovation in eco-design and contributes to a circular economy. The focus is on preventing pollution and minimizing environmental harm at the source, rather than treating symptoms later in the product's life. Question 7. A multinational electronics firm, Innovatech, is developing a new smart home device. To align with ISO 14009-2020 guidelines for integrating environmental aspects into product design and development, the design team is conducting a preliminary life cycle assessment, LCA. They have identified that the primary environmental hotspots during the manufacturing phase are energy-intensive semiconductor fabrication and the use of rare earth elements in the device's components. During the use phase, energy consumption is a significant concern. For the end-of-life phase, potential e-waste generation and the complexity of disassembly for recycling are critical issues. Considering the principles of ISO 14009, Which of the following strategic design interventions would most effectively address these identified environmental hotspots throughout the product's lifecycle? Option A. Prioritize modular design for ease of repair and component upgrade. Select lower power semiconductor technologies and research alternative materials to reduce reliance on rare earth elements, while also designing for efficient disassembly and component recovery at end of life. Option B. Optimize the device's user interface to encourage energy-saving modes and conduct a detailed LCA for the raw material extraction phase only, as this is often the most impactful stage. Option C. Invest heavily in advanced recycling technologies for rare earth elements, increase the device's operational lifespan through robust software updates, and assume that consumer behavior will naturally lead to responsible disposal. Option D. Focus solely on reducing energy consumption during the manufacturing phase by sourcing renewable energy for fabrication plants, and implement a take-back program for end-of-life devices without altering the core product design. The correct answer is A. Prioritize modular design for ease of repair and component upgrade. Select lower power semiconductor technologies and research alternative materials to reduce reliance on rare earth elements, while also designing for efficient disassembly and component recovery at end of life. Explanation: ISO 14009-2020 emphasizes a proactive approach to integrating environmental considerations throughout the product lifecycle, from conception to end of life. When considering the application of life cycle assessment, LCA, within the design and development phases, the standard highlights the importance of identifying significant environmental impacts early. This allows for informed design decisions that can mitigate these impacts. The standard promotes the use of LCA data not just for reporting or compliance, but as a direct input to guide material selection, process optimization, and end-of-life strategies. Specifically, it advocates for the iterative refinement of design based on LCA findings, where potential environmental burdens associated with material extraction, manufacturing, use, and disposal are systematically evaluated. The goal is to achieve a design that minimizes overall environmental performance across all life cycle stages. This involves understanding the trade-offs between different design choices and their associated environmental consequences, a core tenet of effective eco-design as outlined in ISO 14009. For instance, choosing a recycled material might reduce virgin resource depletion, but could potentially increase energy consumption during processing, necessitating a holistic LCA perspective to make the optimal choice. The standard also aligns with regulatory frameworks like the EU's Ecodesign Directive, which mandates consideration of environmental impacts throughout the product lifecycle. Question 8. A company developing a new line of consumer electronics is seeking to align its product development with the principles outlined in ISO 14009-2020. They are in the early conceptualization phase and must decide on the foundational approach for integrating environmental considerations. Which of the following strategies best embodies the proactive, life-cycle-oriented integration encouraged by the standard for minimizing environmental burdens from the outset? Option A. Conducting a comprehensive environmental impact assessment after the initial prototype has been designed to identify and address any significant environmental issues before mass production. Option B. Implementing a robust waste management system at the manufacturing facility to handle production byproducts, without directly linking these efforts to the design choices of the product itself. Option C. Focusing solely on reducing the energy consumption of the product during its operational phase, as this is often the most significant environmental impact for electronic devices. Option D. Embedding environmental performance criteria as mandatory requirements within the product specification document, influencing material sourcing, energy efficiency during use, and end-of-life recyclability from the initial design brief. Correct answer is D. Embedding environmental performance criteria as mandatory requirements within the product specification document, influencing material sourcing, energy efficiency during use, and end-of-life recyclability from the initial design brief. Explanation: the core principle of ISO 14009-2020 is the systematic integration of environmental considerations throughout the product lifecycle, from conception to end of life. This standard, as part of the broader ISO 14000 family, provides guidance on how to embed environmental management into product design and development processes. It emphasizes a proactive approach to minimize environmental impacts by considering factors such as material selection, manufacturing processes, product use, and disposal. The standard encourages organizations to identify and evaluate the environmental aspects associated with their products, setting objectives and targets for improvement. This involves understanding the potential environmental consequences of different design choices and prioritizing those that lead to reduced pollution, resource efficiency, and enhanced recyclability or reusability. For instance, choosing materials with lower embodied energy, designing for disassembly, or minimizing packaging waste are all direct applications of ISO 14009 principles. The standard also promotes the use of life cycle assessment, LCA, as a tool to systematically evaluate environmental impacts at all stages. Compliance and effective implementation are achieved by establishing clear procedures, assigning responsibilities, and ensuring continuous improvement of the environmental performance of products. This holistic approach aims to achieve both environmental benefits and potential economic advantages through innovation and resource optimization. Question 9. When developing product specifications for a new line of portable electronic devices, a design team has identified that the primary environmental impact during the product's use phase is energy consumption. To address this, they aim to set a quantifiable environmental performance target related to this impact. Which of the following approaches best aligns with the principles of ISO 14009-2020 for incorporating this target into the product specifications? Option A. Establishing a target for reduced energy consumption per hour of active use and specifying the use of certified low-power microprocessors and optimized power management software to achieve this. Option B. Including a general statement in the specifications that the product should be energy efficient without defining specific metrics or design mandates. Option C. Mandating the use of recycled materials in the product's casing, as this is a common environmental consideration, irrespective of the identified use phase impact. Option D. Setting a target based on the total energy consumed by the device over its entire expected lifespan, without specifying how this will be measured during the use phase. The correct answer is A. Establishing a target for reduced energy consumption per hour of active use and specifying the use of certified low-power microprocessors and optimized power management software to achieve this. Explanation. The core principle of integrating environmental performance targets into product specifications, as guided by ISO 14009-2020, involves establishing quantifiable and measurable objectives that address the environmental impacts identified throughout the product's life cycle. This process requires a thorough understanding of potential environmental burdens, from raw material extraction to end-of-life management. For instance, if a product's life cycle assessment, LCA, reveals significant energy consumption during its use phase, an environmental performance target might be set for reduced energy usage per unit of output or per hour of operation. This target must be specific, measurable, achievable, relevant, and time-bound. SMART. The specification then translates this target into design requirements, such as mandating the use of energy-efficient components, optimizing operational algorithms, or defining performance benchmarks for prototypes. The selection of appropriate metrics and methodologies for measuring progress against these targets is crucial. This often involves referencing established standards or developing custom measurement protocols that accurately reflect the desired environmental improvement. The iterative nature of product development means these targets and specifications are reviewed and refined as new data emerges or design iterations progress, ensuring continuous improvement in environmental performance. The aim is to embed environmental considerations directly into the decision-making framework of the design process, moving beyond mere compliance to proactive environmental stewardship. Question 10. When a product development team is evaluating the environmental performance of a new electronic device, they identify several potential environmental aspects, including the energy consumption during use, the sourcing of rare earth minerals, the generation of e-waste at end of life, and the emissions from the manufacturing process. According to the principles outlined in ISO 14009-2020 for integrating environmental aspects into product design. Which of the following approaches best guides the prioritization of these aspects for focused design improvements? Option A. Prioritizing aspects based on the perceived public opinion and media coverage surrounding each environmental issue. Option B. Prioritizing aspects based on the immediate cost savings achievable through design modifications, irrespective of the magnitude of the environmental impact. Option C. Prioritizing aspects solely based on the regulatory compliance requirements mandated by the European Union's Restriction of Hazardous Substances, RoHS, Directive. Option D. Prioritizing aspects based on a combined assessment of their potential environmental severity and the organization's level of influence over their management throughout the product's lifecycle. The correct answer is D. Prioritizing aspects based on a combined assessment of their potential environmental severity and the organization's level of influence over their management throughout the product's lifecycle. Explanation: ISO 14009-2020 emphasizes a systematic approach to identifying and prioritizing significant environmental aspects within the product design and development process. This prioritization is crucial for focusing resources on the areas with the greatest potential for environmental improvement. The standard suggests a methodology that considers both the magnitude of the environmental impact and the degree of control or influence the organization has over that aspect. A common framework involves evaluating aspects based on criteria such as severity of impact, e.g., potential for pollution, resource depletion, likelihood of occurrence, and the organization's ability to influence or manage the aspect throughout its life cycle. For instance, an aspect with a severe potential impact that the organization has high control over would likely be considered more significant than an aspect with a minor impact and low control. The objective is to move beyond simple impact assessment to a more strategic prioritization that aligns with the organization's environmental policy and objectives, ensuring that design decisions effectively mitigate the most critical environmental burdens. This aligns with the principle of design for environment by embedding environmental considerations early in the product lifecycle, where changes are most impactful and cost-effective. Question 11. A product development team is tasked with selecting a primary material for a new consumer electronics casing, aiming to align with ISO 14009-2020 principles. They are evaluating several options, including a virgin petroleum-based plastic with high recyclability potential, a bio-based plastic derived from sustainably managed agricultural sources, but with limited end-of-life processing infrastructure, and a recycled aluminum alloy with a known, albeit moderate, energy intensity in its reprocessing. Considering the guidelines for integrating environmental aspects into product design and development, which criterion best encapsulates the holistic approach mandated by ISO 14009-2020 for sustainable material selection? Option A. Focusing solely on materials that meet current legislative restrictions on hazardous substances, without extensive consideration of their broader life cycle, environmental performance, or resource depletion. Option B. Selecting materials that are predominantly derived from renewable resources, irrespective of the energy consumed during their cultivation, processing, or end-of-life management. Option C. Prioritizing materials with the lowest embodied energy across their entire life cycle, including extraction, processing, use, and disposal, while also considering regulatory compliance and circularity potential. Option D. Opting for materials that are easily and widely recyclable, even if their initial production involves significant environmental impacts or the recycled content is low. The correct answer is C. Prioritizing materials with the lowest embodied energy across their entire life cycle, including extraction, processing, use, and disposal, while also considering regulatory compliance and circularity potential. Explanation: ISO 14009-2020 emphasizes a life cycle perspective for environmental management in product design and development. When selecting sustainable materials, a comprehensive approach is required, considering not just the material's inherent properties, but also its entire life cycle impact. This includes resource extraction, manufacturing processes, product use, and end-of-life management. The standard guides organizations to integrate environmental considerations early in the design phase, thereby preventing pollution and minimizing environmental burdens. For instance, A material that requires extensive energy-intensive processing or generates hazardous waste during its production, even if recyclable, might be less preferable than an alternative with a lower overall environmental footprint across all life cycle stages. The selection process should also account for regulatory compliance, such as restrictions on certain substances, e.g., REACH in Europe, and the growing demand for materials that support circular economy principles, like durability, reparability, and recyclability. Therefore, the most effective sustainable material selection criterion is one that holistically evaluates these life cycle impacts and regulatory compliance, rather than focusing on a single attribute. Question 12. When initiating the development of a new portable power bank, what is the most critical element to incorporate into the initial design brief to ensure compliance with emerging global e-waste regulations and facilitate a circular economy approach, as guided by ISO 14009-2020 principles? Option A. A preliminary cost-benefit analysis of potential energy-saving features for the user during the charging process. Option B. Detailed specifications for the recyclability of all constituent materials and the inclusion of a minimum percentage of post-consumer recycled content. Option C. A comprehensive market analysis of competitor product lifespans and warranty periods to inform durability targets. Option D. A qualitative assessment of consumer preferences regarding the aesthetic design and portability of the power bank. The correct answer is B. Detailed specifications for the recyclability of all constituent materials and the inclusion of a minimum percentage of post-consumer recycled content. Explanation. The core principle of integrating environmental aspects into product design and development, as outlined in ISO 14009-2020, is to proactively consider the environmental impacts throughout the entire product lifecycle. This involves embedding environmental considerations from the initial conceptualization and design brief stages. A robust design brief should not merely state functional requirements, but also explicitly define environmental performance targets and constraints. These targets might include specific objectives for material selection, energy efficiency during use, end-of-life recyclability, or reduction of hazardous substances, aligning with regulatory frameworks like the EU's REACH registration, evaluation, authorization and restriction of chemicals, or the Waste Electrical and Electronic Equipment (WEEE) directive. By establishing these environmental parameters upfront, the design process is guided towards solutions that minimize negative environmental consequences. For instance, specifying a target for recycled content in a new electronic device directly influences material sourcing and manufacturing processes. Similarly, setting an energy consumption limit for a home appliance during its operational phase will shape the selection of components and overall product architecture. The design brief acts as the foundational document that communicates these environmental expectations to the design and development teams, ensuring that environmental performance is a key driver of innovation and decision-making, rather than an afterthought. This proactive approach is crucial for achieving genuine environmental improvements and compliance with evolving environmental legislation. Question 13. Considering the principles outlined in ISO 14009-2020 for integrating environmental aspects into product design and development, and focusing on minimizing the energy footprint of an advanced electric vehicle battery throughout its life cycle, which design-centric strategy would most effectively address the significant energy consumption occurring during the product's use phase, particularly in the context of a future advanced battery recycling program? Option A. Establishing a comprehensive and low-emission reverse logistics network to transport used batteries to specialized recycling facilities. Option B. Optimizing the energy consumption of the battery recycling facility itself, incorporating renewable energy sources for its operations. Option C. Developing a highly efficient, closed-loop recycling process for the battery casing materials to maximize resource recovery. Option D. Enhancing the battery's charge-discharge cycle efficiency and extending its operational lifespan through advanced material science and intelligent power management algorithms. Correct answer is D. Enhancing the battery's charge-discharge cycle efficiency and extending its operational lifespan through advanced material science and intelligent power management algorithms. Explanation. The question probes the nuanced application of ISO 14009-2020 principles in managing energy consumption during a product's use phase, specifically when considering a hypothetical advanced electric vehicle (EV) battery recycling program. ISO 14009 emphasizes integrating environmental aspects throughout the product lifecycle, from design to end of life. For an EV battery, the use phase is a significant contributor to its overall environmental footprint, primarily through the energy consumed during charging. While the recycling process itself has energy demands, the guidelines focus on product design and development for reduced environmental impact, means prioritizing strategies that minimize energy use during the product's intended function. Therefore, optimizing the battery's charging efficiency and lifespan directly addresses the use phase energy consumption, a core concern for product design aimed at environmental performance improvement, as per ISO 14009. This involves selecting materials that enhance charge retention, developing intelligent charging algorithms that reduce energy loss, and designing for longevity to delay the need for manufacturing new batteries, thereby reducing the cumulative energy demand across multiple product life cycles. The other options, while relevant to environmental management, do not directly target the use phase energy consumption as the primary integration point for product design improvements as advocated by ISO 14009 in this context. Enhancing the recyclability of the battery casing addresses end of life, but not the operational energy use. Developing a robust reverse logistics network is crucial for recycling, but doesn't inherently reduce the energy consumed by the battery while it's in use. Similarly, focusing solely on the energy intensity of the recycling facility, while important, shifts the focus away from the product's design and its use phase performance. Question 14. When developing an advanced composite material intended for use in high-performance aircraft and considering the requirements of ISO 14009-2020 for integrating environmental aspects into product design, what is the most critical aspect of communicating environmental information to downstream users and end-of-life handlers regarding the material's life cycle? Option A. Communicating the material's potential environmental impacts, safe handling guidelines, and appropriate end-of-life processing methods, considering relevant regulations like REACH. Option B. Offering a comprehensive warranty on the product's performance throughout its intended operational lifespan, irrespective of environmental considerations. Option C. Disclosing the precise percentage of every constituent element, including trace impurities, in a universally accessible public database. Option D. Providing detailed technical specifications of the composite's mechanical properties and manufacturing tolerances. Correct answer is D. Providing detailed technical specifications of the composite's mechanical properties and manufacturing tolerances. Explanation. The core principle of ISO 14009-2020 regarding communication of environmental information to stakeholders during product design and development emphasizes transparency and accessibility. This includes informing downstream users and recyclers about potential environmental impacts and safe handling procedures. For a complex product like an advanced composite material used in aerospace, which may contain trace amounts of hazardous substances or require specialized end-of-life processing, the communication strategy must be comprehensive, providing detailed information on the material's composition, potential ecotoxicity during use or disposal, and recommended recycling or disposal methods ensures that all relevant parties can manage the product's environmental aspects responsibly. This aligns with the directive to consider the entire life cycle and facilitate informed decision-making by all stakeholders, including those involved in maintenance, repair, and end-of-life management. Such communication is vital for complying with regulations like REACH, registration, evaluation, authorization, and restriction of chemicals in Europe, which mandates information dissemination on substances of concern, and for promoting a circular economy by enabling effective material recovery and reuse. The objective is to equip stakeholders with the necessary knowledge to minimize environmental harm throughout the product's existence, from manufacturing to disposal. Question 15. Consider a scenario where a multinational electronics manufacturer, Innovatech, is developing a new portable audio device. To align with ISO 14009-2020 guidelines for integrating environmental aspects into product design and development, Innovatech's design team is evaluating different approaches to minimize the product's lifecycle environmental burden. They are particularly focused on material selection and end-of-life management. Which of the following strategies most comprehensively embodies the proactive integration of environmental considerations throughout the product's design and development lifecycle, beyond mere regulatory compliance like the EU's WEEE directive? Option A. Primarily focusing on sourcing materials that are certified as biodegradable, assuming this inherently minimizes end-of-life impact, and ensuring the product packaging meets basic recyclability standards mandated by local waste management regulations. Option B. Prioritizing the reduction of manufacturing energy consumption by optimizing assembly line processes, and ensuring all product components are sourced from countries with stringent environmental protection laws, without detailed analysis of the product's use phase or end-of-life recyclability. Option C. Conducting a comprehensive life cycle assessment, LCA, to identify environmental hotspots from raw material extraction to disposal, and using these insights to prioritize design choices for material substitution, energy efficiency during use, and design for disassembly, while also establishing internal environmental performance indicators that exceed minimum legal requirements. Option D. Implementing a robust take-back program for used devices, primarily to recover valuable metals for resale, and selecting materials that are readily available from single suppliers to ensure consistent quality, without extensive life cycle impact analysis. The correct answer is C. Conducting a comprehensive life cycle assessment, LCA, to identify environmental hotspots from raw material extraction to disposal, and using these insights to prioritize design choices for material substitution, energy efficiency during use, and design for disassembly, while also establishing internal environmental performance indicators that exceed minimum legal requirements. Explanation: the core principle of integrating environmental aspects into product design and development, as guided by ISO 14009-2020, involves a systematic approach to minimize environmental impact throughout the product's lifecycle. This requires proactive consideration of environmental performance from the initial conceptualization stages through to end-of-life management. The standard emphasizes the importance of identifying and evaluating potential environmental impacts, such as resource depletion, pollution, and waste generation, at each phase of design and development. This proactive assessment allows for informed decision-making to select materials, manufacturing processes, and distribution methods that reduce these impacts. For instance, choosing recycled content or designing for disassembly directly addresses life cycle considerations. The integration is not merely about compliance with regulations like the EU's restriction of hazardous substances, RoHS, directive, which limits certain substances in electrical and electronic equipment, but about embedding environmental thinking into the very fabric of product creation. This involves setting environmental objectives and targets, performing environmental reviews, and utilizing tools like life cycle assessment, LCA, to quantify impacts. The aim is to achieve a balance between functional requirements, economic viability, and environmental stewardship, leading to products that are both innovative and ecologically responsible. The process involves cross-functional collaboration, ensuring that environmental considerations are understood and acted upon by design engineers, material scientists, marketing teams, and procurement specialists. Ultimately, successful integration results in products with a reduced environmental footprint, enhanced market appeal, and improved long-term sustainability. Question 16. A product development team, adhering to the principles of ISO 14009-2020 for integrating environmental aspects into their design and manufacturing strategy, is evaluating various low-impact manufacturing processes for a new metal component. They aim to select a method that demonstrably minimizes energy consumption and material waste during the production phase, thereby reducing the overall environmental footprint of the component. Considering the life cycle perspective advocated by the standard, which manufacturing process would be most aligned with these objectives for shaping metal components with minimal environmental burden? Option A. Hot forging with advanced energy recovery systems. Option B. Additive manufacturing utilizing recycled feedstock. Option C. Cold forming. Option D. Machining with minimal material removal. The correct answer is C. Cold forming. Explanation. The question pertains to the integration of environmental aspects into product design and development, specifically focusing on low-impact manufacturing processes as guided by ISO 14009-2020. The core concept is to identify the manufacturing process that most effectively minimizes environmental burden throughout the product lifecycle, considering energy consumption, waste generation, and material utilization. ISO 14009-2020 emphasizes a life cycle perspective and the selection of processes that reduce environmental impacts at various stages. Cold forming, a process that shapes metal without excessive heating, inherently requires less energy compared to hot forming or casting, which involves significant thermal input and potential for increased emissions and waste from material waste during shaping. Additive manufacturing, while offering design flexibility, can still have substantial energy demands depending on the material and process, and waste can be generated from support structures. Machining, by its nature, removes material, leading to waste in the form of chips and swarf, and often requires cooling lubricants that can pose disposal challenges. Therefore, cold forming aligns best with the principles of minimizing environmental impact in manufacturing as outlined in ISO 14009-2020. By reducing energy consumption and material waste during the shaping phase. Question 17. A firm is developing a new generation of electric vehicle charging stations. To align with ISO 14009-2020 guidelines for integrating environmental aspects into product design, what is the most comprehensive method for identifying potential environmental aspects and their impacts throughout the product's life cycle, particularly concerning the end-of-life phase and relevant regulatory frameworks? Option A. Focusing solely on the energy efficiency during the product's operational use phase and ensuring the packaging materials are easily recyclable according to local municipal waste guidelines. Option B. Prioritizing the reduction of volatile organic compound (VOC) emissions during the manufacturing process and selecting materials with low embodied energy without extensive end-of-life analysis. Option C. Performing a preliminary environmental review based on common industry practices for electronic goods and ensuring compliance with general product safety standards. Option D. Conducting a detailed life cycle assessment (LCA) that explicitly maps material flows, energy consumption, and waste generation for each stage, with specific attention to the recyclability of components and compliance with e-waste regulations like the WEEE directive. The correct answer is D. Conducting a detailed life cycle assessment (LCA) that explicitly maps material flows, energy consumption, and waste generation for each stage, with specific attention to the recyclability of components and compliance with e-waste regulations like the WEEE directive. Explanation. The process of identifying environmental aspects and their associated impacts within product design and development, as guided by ISO 14009-2020, necessitates a systematic approach that considers the entire life cycle of a product. Environmental aspects are elements of an organization's activities, products, or services that can interact with the environment. Environmental impacts are any change to the environment, whether adverse or beneficial, wholly or partially resulting from an organization's aspects. For a complex product like an electric vehicle charging station, a thorough assessment must go beyond mere operational emissions. It involves scrutinizing raw material extraction, manufacturing processes, transportation, installation, use phase, energy consumption, potential leaks of refrigerants if applicable, electromagnetic interference, maintenance and end-of-life treatment, disposal, recycling, remanufacturing. When evaluating the end-of-life phase, the focus is on the fate of materials, potential for hazardous substances to be released, and the energy required for disassembly and recycling. For instance, the presence of rare earth elements in electronic components, the energy intensity of recycling specific alloys, or the potential for leaching of heavy metals from discarded circuit boards are all critical considerations. Understanding the regulatory landscape, such as the Waste Electrical and Electronic Equipment (WEEE) directive in the European Union or similar national regulations concerning e-waste, is also crucial for informing design decisions that facilitate compliance and minimize environmental burden. Therefore, a comprehensive identification involves mapping out all potential environmental interactions across all stages, from cradle to grave, and assessing their significance based on criteria like severity, duration, and reversibility of the impact. This systematic identification forms the foundation for integrating environmental considerations into design choices, aiming to prevent or reduce negative impacts and enhance positive ones. Question 18. A product development team is tasked with redesigning an electronic device to reduce its environmental footprint, specifically focusing on eliminating the use of certain brominated flame retardants, BFR, due to regulatory pressures and consumer demand. They are exploring alternative materials. Which of the following strategies best aligns with the principles of ISO 14009-2020 for substituting hazardous substances in product design, considering a holistic approach to environmental management? Option A. Conducting a comprehensive life cycle assessment to evaluate the environmental performance of potential BFR alternatives across their entire life cycle, including the assessment of any new potential hazards introduced by the substitutes and ensuring compatibility with manufacturing processes and overall product performance. Option B. Focusing solely on meeting the minimum legal requirements for hazardous substance elimination as stipulated by regulations like RoHS, and prioritizing substitutes that offer the most significant cost reduction in manufacturing, even if their environmental profile is only marginally better. Option C. Prioritizing substitutes that have been historically used in similar product categories, assuming their safety and environmental compatibility based on past applications, without conducting new assessments or considering evolving regulatory landscapes and scientific understanding of chemical impacts. Option D. Immediately replacing the BFRs with the most readily available and cost-effective non-halogenated organic compounds that are not currently subject to specific restrictions, without further investigation into their long-term environmental fate or potential health impacts. The correct answer is A. Conducting a comprehensive life cycle assessment to evaluate the environmental performance of potential BFR alternatives across their entire life cycle, including the assessment of any new potential hazards introduced by the substitutes, and ensuring compatibility with manufacturing processes and overall product performance. Explanation. The core principle of substituting hazardous substances in product design, as guided by ISO 14009-2020, involves a multifaceted approach that prioritizes environmental and human health benefits while maintaining product functionality and economic viability. This process necessitates a thorough life cycle assessment, LCA, to identify the specific hazardous substances present and their potential environmental impacts at each stage, from raw material extraction to end-of-life disposal. The selection of alternatives is not solely based on the absence of a particular hazard, but also on the potential for new, unforeseen environmental or health risks associated with the substitute. Therefore, a robust risk assessment of potential replacements is paramount. Furthermore, the feasibility of implementing the substitution must be evaluated, considering factors such as availability of the alternative material, its compatibility with existing manufacturing processes, and the cost implications. Regulatory compliance, such as adherence to directives like the EU's Restriction of Hazardous Substances, RoHS, or REACH registration, evaluation, authorization, and restriction of chemicals, often drives the initial identification of substances for substitution. However, a proactive approach guided by ISO 14009 goes beyond mere compliance, aiming for continuous improvement by seeking inherently safer and more environmentally benign materials. The ultimate goal is to achieve a net positive environmental outcome, which means the benefits of substitution, considering all life cycle impacts, outweigh any potential drawbacks or the impacts of the original substance. Question 19. A manufacturing firm specializing in modular office furniture is undertaking a product redesign initiative to align with ISO 14009-2020 guidelines, with a specific focus on minimizing material consumption. Considering the life cycle of their products, which design strategy would most effectively achieve a substantial reduction in overall material input while maintaining product integrity and market competitiveness? Option A. Implementing a design for disassembly and repairability, coupled with the use of higher density, recycled composite materials for structural components. Option B. Solely focusing on replacing all virgin plastics with bio-based polymers, irrespective of their durability or end-of-life processing requirements. Option C. increasing the thickness of all metal framing to enhance perceived durability, even if current performance metrics indicate sufficient strength. Option D. Reducing the number of fasteners and adhesives by welding all components together permanently, thereby eliminating the possibility of repair or component replacement. The correct answer is A. Implementing a design for disassembly and repairability, coupled with the use of higher density, recycled composite materials for structural components. Explanation: the core principle of reducing material consumption in product design, as guided by ISO 14009-2020, involves a multifaceted approach that extends beyond simple material substitution. It necessitates a deep understanding of the entire product lifecycle and its associated environmental impacts. This includes critically evaluating the necessity of each component and the material's performance characteristics. Strategies such as designing for disassembly, modularity, and repairability directly contribute to reducing the demand for new materials by extending product lifespan and facilitating the recovery of components. Furthermore, optimizing product functionality to achieve the same or better performance with less material, often through advanced engineering and material science, is a key element. This also encompasses minimizing material waste during manufacturing processes, which is intrinsically linked to efficient design. The concept of dematerialization, where a product delivers the same utility with less physical substance, is a paramount objective. For instance, a company developing a new portable electronic device would consider how to reduce the plastic housing, the amount of rare earth metals in its components, and the packaging material, while ensuring durability and user experience. This aligns with the principles of eco-design and circular economy, aiming to lessen the environmental burden from raw material extraction to end-of-life management. The emphasis is on a holistic view of material efficiency throughout the value chain. Question 20. A manufacturing firm developing a new line of electronic devices is committed to adhering to ISO 14009-2020 principles for environmental management in product design. Their objective is to significantly reduce waste generation and prevent pollution throughout the product's lifecycle. Considering the hierarchy of waste management and pollution prevention strategies outlined in the standard, which of the following design-focused approaches would yield the most substantial and proactive environmental benefit? Option A. Implementing design for disassembly and modularity to facilitate the recovery and remanufacturing of components at end of life. Option B. Specifying the use of recycled content for all plastic and metal parts in the device. Option C. Prioritizing the reduction of material usage and the elimination of hazardous substances during the initial concept and material selection phases. Option D. Establishing a take-back program for used devices to ensure they are properly processed through licensed recycling facilities. The correct answer is A. Implementing design for disassembly and modularity to facilitate the recovery and remanufacturing of components at end of life. Explanation: the core principle of ISO 14009-2020 regarding waste management and pollution prevention within product design is to prioritize strategies that minimize environmental impact throughout the product lifecycle. This involves a hierarchical approach. The most effective strategy is to prevent waste generation at the source, which means designing products and processes to use fewer materials, less hazardous substances, and to create less waste during manufacturing and end of life. Following this, the guideline emphasizes reuse, where components or the entire product can be used again for its original purpose. Recycling is the next preferred option, where materials are reprocessed into new products. Recovery, such as energy recovery from waste, is considered when the above options are not feasible. Finally, disposal, such as landfilling or incineration without energy recovery, is the least preferred option and should be minimized. The question asks for the most impactful approach to waste management and pollution prevention, as per ISO 14009-2020 guidelines. Considering the hierarchy, preventing waste at the source is the most proactive and environmentally beneficial strategy, as it avoids the creation of waste altogether, thereby also preventing the potential pollution associated with its management and disposal. This aligns with the life cycle thinking and eco-design principles promoted by the standard, which aim to reduce environmental burdens from the earliest stages of product development. Question 21. When integrating environmental considerations into the design of a new consumer appliance, What primary criterion should guide the selection of materials, according to the principles outlined in ISO 14009-2020, considering the entire product lifecycle and potential regulatory implications? Option A. The ease of processing and manufacturing the material, which can lead to faster production cycles and reduced manufacturing energy consumption. Option B. A comprehensive assessment of the material's environmental footprint across its entire life cycle, including resource extraction, manufacturing, use, and end-of-life management, while also evaluating its potential for reuse, recycling, or safe degradation, and ensuring compliance with chemical substance regulations. Option C. The material's aesthetic appeal and perceived quality by consumers, as this drives market demand and product adoption. Option D. The lowest initial cost of the raw material, as this directly impacts the product's market competitiveness and accessibility for consumers. Correct answer is B. A comprehensive assessment of the material's environmental footprint across its entire life cycle, including resource extraction, manufacturing, use, and end-of-life management, while also evaluating its potential for reuse, recycling, or safe degradation, and ensuring compliance with chemical substance regulations. Explanation. ISO 14009-2020 emphasizes a life cycle perspective in product design, which includes the selection of materials. When evaluating materials for improved environmental performance, a holistic approach is necessary, considering impacts from extraction through disposal. The standard promotes the reduction of hazardous substances, the use of recycled content, and the selection of materials that facilitate easier disassembly and recycling at the end of the product's life. Furthermore, it advises considering the energy and resource intensity of material processing and manufacturing. For a hypothetical scenario involving the development of a new electronic device, a designer must balance several material attributes. The selection of a bio-based polymer for casing components, while potentially reducing reliance on fossil fuels, must be weighed against its durability, recyclability, and potential for leaching of additives compared to a high recycled content engineered plastic. The standard encourages the use of life cycle assessment, LCA, principles to inform these decisions, even if a full LCA is not performed. Therefore, the most comprehensive criterion for material selection, aligning with ISO 14009-2020, is the one that addresses the broadest range of environmental impacts across the product's life cycle, including resource depletion, energy consumption, emissions, waste generation, and potential for reuse or recycling, while also considering regulatory compliance, such as REACH registration, evaluation, authorization, and restriction of chemicals for chemical substances. The consideration of a material's potential to contribute to a circular economy by being easily reprocessed or biodegraded safely is also a key aspect. Question 22. Consider a hypothetical electronic device manufacturer, Innovatec, aiming to improve the end-of-life management of their new smart home hub. They are evaluating different design strategies to enhance disassembly and recyclability in line with ISO 14009-2020 guidelines. Which of the following design choices would most effectively contribute to achieving these goals by facilitating efficient material separation and component recovery? Option A. Employing a modular design with standardized, tool-less connectors for major subassemblies and clearly labeling component materials for easier sorting. Option B. Utilizing a single, robust casing material that is highly durable throughout the product's intended use, even if it requires specialized tools for separation. Option C. Focusing solely on energy efficiency during the product's operational phase, with minimal consideration for its physical construction or end-of-life disassembly. Option D. Integrating components directly into the main chassis, using permanent bonding techniques to ensure structural integrity and reduce the number of distinct parts. The correct answer is A. Employing a modular design with standardized, tool-less connectors for major subassemblies and clearly labeling component materials for easier sorting. Explanation. ISO 14009-2020 emphasizes integrating environmental considerations throughout the product lifecycle, from conception to end of life. Design for disassembly, DFD, is a key strategy within this framework, aiming to facilitate the separation of product components at the end of its useful life. This process is crucial for maximizing material recovery, enabling reuse of parts, and simplifying recycling efforts, thereby minimizing waste and resource depletion. When considering DFD, the choice of fastening mechanisms is paramount. For instance, using snap fits or easily removable screws over permanent adhesives or complex welding techniques significantly enhances a product's end-of-life manageability. Furthermore, material selection plays a vital role. Grouping similar materials together or using easily separable composite materials aids in the sorting and processing stages of recycling. The standard encourages a holistic approach, where DFD is not an afterthought but an integral part of the design process, informed by anticipated disassembly and recycling challenges. This proactive integration helps in complying with evolving environmental regulations, such as the EU's Ecodesign Directive, which increasingly mandates product repairability and recyclability. Therefore, a design that prioritizes easily separable components, compatible material groupings, and standardized fasteners directly supports the principles of DFD and enhances overall recyclability, aligning with the overarching goal of sustainable product development as outlined in ISO 14009-2020. Question 23. When a multinational electronics firm, Novatech, aims to embed energy efficiency principles into the design of its next generation of smart home devices, aligning with ISO 14009-2020 guidelines, which of the following design integration strategies would most directly address the standard's emphasis on product-level energy performance throughout its life cycle? Option A. Implementing a take-back program that facilitates the energy-efficient recycling and material recovery of devices at the end of their operational lifespan. Option B. Redesigning internal circuitry and power management algorithms to minimize standby power consumption and optimize operational energy use during active states. Option C. Committing to sourcing all manufacturing components from suppliers who utilize renewable energy sources for their production facilities. Option D. Developing innovative packaging solutions that incorporate biodegradable materials and are optimized for reduced shipping volume and weight. The correct answer is B. Redesigning internal circuitry and power management algorithms to minimize standby power consumption and optimize operational energy use during active states. Explanation: the core principle of integrating energy efficiency into product design under ISO 14009-2020 involves a life cycle perspective. This means considering energy consumption not just during the use phase, but also during manufacturing, distribution, and end-of-life stages. While improving the energy source, e.g., switching to renewables, is a valid environmental strategy, it is not directly a design integration activity for the product itself, as per the standard's focus on product attributes. Similarly, optimizing packaging to reduce transport emissions, while important for overall environmental performance, is a supporting element rather than the primary product design integration for energy efficiency. Focusing solely on end-of-life energy recovery misses the significant opportunity to reduce energy demand throughout the product's lifespan, which is a key objective of the standard. Therefore, the most direct and impactful integration of energy efficiency into product design, as guided by ISO 14009-2020, is through enhancing the inherent energy performance of the product's components and operational logic during its use phase. This aligns with the standard's emphasis on proactive design choices that minimize environmental impact across the product's life cycle, with a particular focus on resource efficiency and pollution prevention. The standard encourages design teams to explore material selection, manufacturing processes, and operational modes that inherently reduce energy consumption. Question 24. A multinational electronics corporation, Innovate Tech, is embarking on the development of a new generation of smart home hubs. To align with its corporate sustainability goals and adhere to the principles outlined in ISO 14009-2020, Innovate Tech aims to significantly reduce the product's environmental impact across its entire lifecycle. Considering the guidelines for integrating environmental aspects into product design and development, which of the following strategic approaches would be most effective in achieving Innovate Tech's objective, particularly in addressing resource depletion and end-of-life waste challenges? Option A. Implementing a robust take-back and recycling program only after the product has been launched and is in the market to manage end-of-life issues. Option B. Conducting a comprehensive life cycle assessment, LCA, during the initial conceptualization and design phases to inform material selection, manufacturing processes, and end-of-life strategies. Option C, focusing solely on optimizing the energy efficiency of the smart home hub during its use phase, as this stage typically has the largest operational environmental impact. Option D, engaging in extensive post-production environmental audits to identify areas for improvement in manufacturing and distribution after the product has been finalized. The correct answer is B, conducting a comprehensive life cycle assessment, LCA, during the initial conceptualization and design phases to inform material selection, manufacturing processes, and end-of-life strategies. Explanation: the integration of life cycle assessment, LCA, into product design and development, as guided by ISO 14009-2020, aims to proactively identify and mitigate environmental impacts throughout a product's entire existence. This involves a systematic approach that considers all stages, from raw material extraction and manufacturing to distribution, use, and end-of-life management. When a company is developing a new electronic device and wants to ensure its design minimizes potential environmental burdens, particularly concerning resource depletion and waste generation, the most effective strategy, aligned with ISO 14009 principles, is to embed LCA considerations directly into the early design phases. This proactive integration allows for informed decisions regarding material selection, component sourcing, energy efficiency during use, and the feasibility of repair, refurbishment, or recycling. For instance, choosing materials with lower embodied energy, designing for disassembly, and specifying components that can be easily upgraded or replaced contribute significantly to reducing the overall environmental footprint. This contrasts with reactive measures, or focusing solely on one life cycle stage, which would likely miss critical opportunities for improvement and could lead to higher overall environmental costs. The standard emphasizes a holistic view, making early-stage integration paramount for achieving genuine environmental performance improvements in product design. Question 25. Consider a scenario where a consumer electronics manufacturer is developing a new smart television. To align with ISO 14009-2020 guidelines for integrating environmental aspects into product design and development, particularly concerning end-of-life management, which design strategy for component separation would most effectively support the principles of design for disassembly and facilitate subsequent material recovery and recycling efforts, while also considering potential regulatory requirements like the WEEE directive. Option A, encasing all electronic components within a sealed, non-separable resin to protect them from environmental factors during operation. Option B, utilizing snap-fit connectors and clearly labeled, easily removable fasteners that require only standard screwdrivers for disassembly. Option C, employing high-strength adhesives and ultrasonic welding for all major component assemblies to ensure structural integrity during use. Option D, integrating components directly onto a single printed circuit board with no modular sub-assemblies to minimize the number of individual parts. Correct answer is B, utilizing snap-fit connectors and clearly labeled, easily removable fasteners that require only standard screwdrivers for disassembly. Explanation: the core principle of design for disassembly, DFD, within the framework of ISO 14009-2020 emphasizes facilitating the separation of product components at the end of its life to enable reuse, recycling, or safe disposal. This involves considering how a product can be easily taken apart without specialized tools or excessive force, thereby minimizing the environmental burden associated with dismantling. Key aspects include the selection of fastening methods that allow for easy removal, avoiding permanent joining techniques like welding or strong adhesives where possible, and designing for modularity so that functional sub-assemblies can be separated. Furthermore, material identification and labeling are crucial to guide disassembly and sorting processes, aligning with directives such as the EU's Waste Electrical and Electronic Equipment (WEEE) directive, which mandates collection and recycling targets and influences design choices for ease of processing. The goal is to maximize the recovery of valuable materials and minimize the volume of waste sent to landfill or incineration, directly contributing to circular economy principles and reducing the product's overall life cycle environmental impact. Therefore, prioritizing ease of component separation through appropriate design choices is paramount. Question 26. When integrating recycled content into product design, what is the most critical consideration for an organization seeking to align with the principles outlined in ISO 14009-2020, specifically concerning the overall environmental performance and lifecycle impact? Option A. Compliance with the minimum legal requirements for recycled content mandated by regional regulations, without further environmental due diligence. Option B. Ensuring the recycled material meets aesthetic requirements and consumer perception for market acceptance, regardless of its underlying environmental profile. Option C. Prioritizing the highest possible percentage of recycled content, even if it necessitates the use of more energy-intensive reprocessing techniques or compromises product durability. Option D. A comprehensive life cycle assessment, LCA, to evaluate the net environmental benefit of using recycled materials, accounting for potential contaminants and processing impacts against virgin material alternatives. Correct answer is D. A comprehensive life cycle assessment, LCA, to evaluate the net environmental benefit of using recycled materials, accounting for potential contaminants and processing impacts against virgin material alternatives. Explanation. ISO 14009-2020 emphasizes the integration of environmental considerations throughout the product lifecycle, from conception to end of life. When considering the use of recycled content materials in product design, several factors are crucial. The standard guides organizations to assess the environmental benefits of recycled materials, such as reduced resource depletion and lower embodied energy compared to virgin materials. However, it also mandates a thorough evaluation of potential trade-offs. These trade-offs can include variations in material performance, the presence of contaminants that might affect recyclability or product safety, and the energy or chemical processes required for recycling and reincorporation. For instance, if a recycled plastic contains additives that hinder its future recyclability or leach harmful substances, its overall environmental benefit is diminished, potentially contravening the principles of a circular economy that ISO 14009 supports. Therefore, a holistic assessment that balances the advantages of recycled content with its potential technical and environmental drawbacks is essential for making informed design decisions aligned with the standard's objectives. This includes understanding the supply chain for recycled materials and ensuring their quality and consistency. Question 27. Consider the development of a new line of portable power banks. The design team is tasked with setting specific environmental performance targets for the product's lifecycle, adhering to the principles outlined in ISO 14009-2020. They have identified potential impacts related to the extraction of rare earth minerals for battery components, the energy consumed during charging and discharging, and the end-of-life management of the device. Which of the following approaches most effectively integrates these identified environmental aspects into concrete product specifications to drive improved environmental performance? Option A. Establishing a target to reduce the embodied energy of the casing material by 20% and ensuring that at least 75% of the device's components are designed for disassembly and potential recycling, with a clear directive for suppliers to provide documentation on the origin of critical raw materials. Option B. Focusing solely on achieving an ENERGY STAR certification for the device's charging efficiency and setting a vague goal of minimizing e-waste, without quantifiable targets for material content or end-of-life processes. Option C. Mandating the use of recycled plastics for the casing and requiring a minimum 10% reduction in the overall weight of the power bank compared to previous models, without specific metrics for component recyclability or raw material sourcing. Option D. Implementing a policy that prioritizes the use of locally sourced materials whenever possible and setting a broad objective to decrease the carbon footprint of the manufacturing process by an unspecified percentage. The correct answer is A. Establishing a target to reduce the embodied energy of the casing material by 20% and ensuring that at least 75% of the device's components are designed for disassembly and potential recycling, with a clear directive for suppliers to provide documentation on the origin of critical raw materials. Explanation. The core principle of integrating environmental performance targets into product specifications is guided by ISO 14009-2020, involves establishing measurable and achievable goals that address the environmental impacts identified throughout the product's life cycle. This process requires a thorough understanding of the product's potential environmental burdens, from raw material extraction and manufacturing to use and end-of-life disposal. These targets should be specific, measurable, achievable, relevant, and time-bound. SMART, ensuring they are actionable and contribute to the overall environmental objectives of the organization. For instance, a target might be to reduce the energy consumption of a consumer electronic device by 15% during its use phase, or to increase the recyclability of a packaging material to 80% by weight. The selection and definition of these targets are informed by various factors, including regulatory requirements, stakeholder expectations, technological feasibility, and the organization's environmental policy. The integration of these targets into product specifications ensures that environmental considerations are embedded from the initial design stages, influencing material selection, manufacturing processes, and product design choices to minimize negative environmental outcomes. This proactive approach aligns with the principles of eco-design and sustainable product development, aiming to improve the environmental performance of products over time and contribute to a more circular economy. The process necessitates collaboration across different departments, including design, engineering, procurement, and marketing, to ensure alignment and successful implementation. Question 28. Consider a multinational electronics manufacturer, Innovatech, which is developing a new generation of portable computing devices. To align with ISO 14009-2020 guidelines for integrating environmental aspects into product design, Innovatech's design team is evaluating different strategies to minimize the product's overall environmental footprint. Which of the following approaches most effectively embodies the proactive integration of environmental considerations throughout the product's life cycle, considering both design choices and compliance with regulations like the Restriction of Hazardous Substances, RoHS? Option A. Implementing a robust end-of-life recycling program after the product has been designed and manufactured, ensuring that collected devices are properly processed, without significant prior consideration of design for disassembly or material recyclability during the initial design stages. Option B. Focusing solely on reducing energy consumption during the product's use phase, as this is often the most significant contributor to the product's operational environmental impact, and addressing material choices only if they directly affect energy efficiency. Option C. Conducting a comprehensive life cycle assessment, LCA, during the conceptual design phase to identify environmental hotspots, and then using these findings to inform material selection, manufacturing processes, and end-of-life strategies, ensuring compliance with directives like RoHS by prioritizing the use of compliant components and materials. Option D. Primarily relying on external certifications and eco-labels for the finished product to signal its environmental performance, with internal design processes having minimal emphasis on proactively identifying and mitigating environmental impacts during development. The correct answer is C. Conducting a comprehensive life cycle assessment, LCA, during the conceptual design phase to identify environmental hotspots, and then using these findings to inform material selection, manufacturing processes, and end-of-life strategies, ensuring compliance with directives like RoHS by prioritizing the use of compliant components and materials. Explanation: the core principle of integrating environmental aspects into product design and development, as guided by ISO 14009-2020, is to proactively address potential environmental impacts throughout a product's life cycle. This involves a systematic approach to identify, evaluate, and manage these impacts from the initial concept phase through to end-of-life management. A key aspect of this integration is ensuring that environmental considerations are not merely an afterthought, but are embedded within the decision-making processes at each stage of design and development. This proactive stance allows for the selection of materials with lower embodied energy, the design of products for disassembly and recyclability, and the minimization of waste generation during manufacturing and use. Furthermore, it necessitates an understanding of relevant environmental legislation, such as the EU's Restriction of Hazardous Substances, RoHS, directive, which dictates limitations on specific hazardous materials in electrical and electronic equipment. thereby influencing material selection and design choices. The goal is to achieve environmental improvements by influencing design decisions early on, which is generally more effective and less costly than attempting to remediate environmental issues after a product has been designed or manufactured. This holistic perspective, often referred to as eco-design or sustainable design, aligns with the broader principles of environmental management systems that aim for continuous improvement in environmental performance. Question 29. A company is developing a new generation of portable audio players and seeks to align its design process with ISO 14009-2020 guidelines, specifically focusing on minimizing energy consumption throughout the product's lifecycle. They are debating between two primary charging interface options: a proprietary high-current direct connection to a dedicated AC adapter, or a universal USB-C power delivery (PD) interface. Considering the standard's emphasis on lifecycle thinking and energy efficiency, which charging interface approach would be most consistent with the spirit and intent of ISO 14009-2020 for this type of consumer electronic device? Option A. Implementing a USB-C power delivery (PD) interface to leverage potential system-wide energy efficiencies and user flexibility in power source selection. Option B. Focusing solely on the energy efficiency of the internal battery technology, assuming the charging interface has a negligible impact on overall lifecycle energy consumption. Option C. Utilizing a proprietary direct connection to a dedicated AC adapter designed for maximum charging speed, regardless of potential energy conversion losses during use. Option D. Adopting a low-power, slow-charging AC adapter that minimizes heat generation during charging, even if it significantly increases the time required to fully charge the device. Correct answer is A. Implementing a USB-C power delivery (PD) interface to leverage potential system-wide energy efficiencies and user flexibility in power source selection. Explanation: the core principle of integrating energy efficiency into product design, as guided by ISO 14009-2020, involves a life cycle perspective. This means considering energy consumption not just during the product's use phase, but also during its manufacturing, distribution, and end-of-life stages. When evaluating design choices for a new portable electronic device, a key consideration is the energy source for charging. While a direct AC adapter offers convenience and potentially higher initial charging speeds, its energy conversion losses can be significant. A USB-C power delivery (PD) system, especially when paired with optimized charging circuitry within the device and the adapter, can offer more granular control over power flow and potentially higher overall system efficiency, minimizing wasted energy. Furthermore, ISO 14009 emphasizes considering the embodied energy in materials and manufacturing processes. While the USB-C PD system might involve slightly more complex internal components, the potential for reduced energy consumption over the product's life cycle, coupled with the flexibility for users to utilize existing, potentially more efficient, USB-C power sources, aligns better with the standard's holistic approach to environmental aspects. The directive to minimize energy consumption throughout the product's life cycle, including the use phase, makes the USB-C PD approach, with its inherent potential for efficiency gains and user-side flexibility, the most aligned strategy with ISO 14009-2020 guidance for this specific product category. Question 30. A manufacturing firm is developing a new line of industrial cleaning agents. During the product development phase, a critical review of potential environmental impacts reveals that the formulation process can lead to volatile organic compound (VOC) emissions into the air and residual chemical compounds in wastewater discharge. The company is committed to adhering to the principles of ISO 14009-2020 for integrating environmental aspects into product design. Considering the life cycle perspective and the goal of pollution prevention, which design strategy would most effectively address these identified emission concerns in alignment with the standard's guidelines? Option A. Prioritize the selection of biodegradable solvents with low vapor pressure for the cleaning agent formulation, and design the packaging to include a concentrated formula requiring dilution with water at the point of use, thereby minimizing the volume of active chemicals released. Option B. Conduct extensive life cycle impact assessments only after the product prototype is finalized to identify areas for improvement in emission control during the manufacturing stage. Option C. Implement advanced air filtration systems at the manufacturing facility to capture VOCs and invest in a robust on-site wastewater treatment plant to remove residual chemicals before discharge. Option D. Focus on developing detailed end-of-life disposal instructions for consumers to ensure proper handling of the product and its packaging, thereby mitigating downstream environmental releases. The correct answer is A. Prioritize the selection of biodegradable solvents with low vapor pressure for the cleaning agent formulation, and design the packaging to include a concentrated formula requiring dilution with water at the point of use, thereby minimizing the volume of active chemicals released. Explanation: the core principle of integrating environmental aspects into product design, as guided by ISO 14009-2020, involves a proactive approach to minimizing negative impacts throughout the product's life cycle. When considering emissions to air and water, the standard emphasizes identifying and controlling these potential environmental aspects at the earliest stages of design. This includes selecting materials that inherently produce fewer harmful airborne or waterborne byproducts during manufacturing, use, and disposal. Furthermore, the design process should incorporate features that prevent or mitigate the release of pollutants. For instance, specifying closed-loop systems for manufacturing processes or designing products with integrated filtration mechanisms for their operational phase directly addresses the control of emissions. Legal frameworks, such as the Clean Air Act or the Clean Water Act in various jurisdictions, often set permissible emission limits. ISO 14009-2020 encourages exceeding these minimum requirements through design choices that aim for pollution prevention rather than mere compliance. Therefore, the most effective strategy involves a holistic life cycle assessment to anticipate and engineer out potential emission sources, prioritizing prevention through material selection and process design, and incorporating technologies that capture or neutralize pollutants before release. This aligns with the directive to integrate environmental considerations into the very fabric of product development, ensuring that environmental performance is a key design parameter, not an afterthought.